Hello there, and welcome. I'm so glad you found your way here tonight. Maybe you had a long day, or maybe you're the kind of person who finds peace in cosmic wonders rather than counting sheep. Either way, you've come to the right place. Tonight, we're drifting through clouds, not the familiar ones that float across Earth's sky, but something far more ancient, far more vast. We're traveling through nebulas, those immense cosmic clouds that paint the universe in colors we can barely imagine. These are the places where stars are born and where they die. They're nurseries and graveyards, beginnings and endings, all swirling together in the quiet darkness of space. You don't need to do anything but rest. Let your breathing slow. Let your thoughts drift. We'll move gently through these celestial clouds, discovering their secrets one by one as you settle deeper into sleep. And before we begin our journey, if these peaceful explorations help you unwind, or if they give you a quiet way to end your day, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. Let's begin. The word nebula comes from Latin, meaning cloud or fog. And when early astronomers looked through their first telescopes, that's exactly what these objects seemed to be. Fuzzy patches of light scattered across the darkness, indistinct and mysterious. They had no idea what they were seeing. Some thought perhaps these were merely clouds within our atmosphere, illuminated by some unknown source. Others wondered if they might be distant collections of unresolved stars, too faint and far away to distinguish individually. For centuries, any diffuse object in the night sky earned the name nebula. The Andromeda Galaxy was once called the Andromeda Nebula. Spiral galaxies were known as spiral nebulae. It wasn't until the early 20th century when astronomers like Edwin Hubble began to resolve individual stars within some of these objects that we understood the truth. Some nebulae were indeed entire galaxies, island universes containing hundreds of billions of stars, but others were something different entirely. True nebulas as we understand them today are clouds of gas and dust within our own Milky Way galaxy. They exist in the space between stars, that vast emptiness we call the interstellar medium. And they are anything but empty. These clouds are made mostly of hydrogen, the simplest and most abundant element in the universe, along with helium and traces of heavier elements. Mixed throughout are tiny grains of dust, particles of carbon, silicates and frozen molecules no larger than smoke. The scale of nebulas defies easy comprehension. Some span just a few light years across. Others stretch for hundreds of light years, containing enough material to birth thousands of suns. To give you a sense of this vastness, consider that a single light year is nearly 6 trillion miles. The distance light travels in an entire year. And some nebulas extend across dozens or even hundreds of these incomprehensible distances. Yet, despite their enormous size, nebulas are incredibly diffuse. On average, the interstellar medium contains only about 1 atom per cubic centimeter. That's far emptier than the best vacuum we can create on Earth. But in certain places, conditions conspire to gather this material together. Gravity begins its patient work, pulling atoms closer. Dust grains collide and stick together. Over millions of years, these sparse regions become denser, forming the clouds we call nebulas. The closest known nebula to Earth is the Helix Nebula, a planetary nebula lying about 650 light-years away in the constellation Aquarius. Even at this relatively nearby distance, the light we see from the helix left that cloud during the late Middle Ages on Earth, long before telescopes existed to observe it. When we look at nebulas, we're not seeing them as they are now, but as they were hundreds or thousands of years ago. We're looking backward through time, watching ancient light finally complete its long journey to our eyes. In the early 17th century, a French lawyer and amateur astronomer named Nicolas Claude Fabry de Peresque became the first person to observe a nebula through a telescope. The object he saw was the Orion Nebula, a vast stellar nursery hanging in space like a glowing cloud behind Orion's sword. Though Peresque didn't understand what he was looking at, he had opened a door. Other astronomers followed, each adding to our catalogue of these mysterious objects. By 1715, the English astronomer Edmund Halley, famous for the comet that bears his name, had compiled a list of 6 nebulas. Over the following decades, that number grew. Charles Messier, a French astronomer obsessed with hunting comets, created a more extensive catalogue. He wanted to document all the fuzzy objects that might be mistaken for comets, so he wouldn't waste his time observing them repeatedly. His catalogue, published in 1781, contained over 100 objects, many of which were nebulas. Today we still refer to many nebulas by their Messier numbers. The Orion Nebula is M42, the Eagle Nebula is M16, the Crab Nebula is M1. But it wasn't until the late 19th and early 20th centuries that we began to understand what nebulas truly were. With the development of spectroscopy, astronomers could analyze the light from these clouds, breaking it down into its component colors like a prism splitting sunlight into a rainbow. What they found was revolutionary. Some nebulas showed bright emission lines, specific colors of light corresponding to particular elements being heated and excited. Others showed absorption lines where certain colors were missing, blocked by cold dust. And still others reflected the light of nearby stars, scattering it like fog around a street lamp. Each type of nebula told a different story. Each was a chapter in the vast narrative of stellar birth and death playing out across the galaxy. There are several distinct types of nebulas, each with its own character and origin. Understanding these different varieties is like learning to recognize different species in a cosmic ecosystem. Each has its place, its purpose, its role in the grand cycle of matter and energy that shapes the universe. Emission nebulas are perhaps the most visually stunning. These are vast clouds of gas, mostly hydrogen, that glow with their own light. They appear in photographs as swirling regions of red, pink and purple, like cosmic watercolors painted across space. The mechanism behind their glow is elegant. Deep within these clouds, young, massive stars are being born. These stars are extraordinarily hot, with surface temperatures exceeding 25,000 degrees. They pour out intense ultraviolet radiation, flooding the surrounding gas with energetic photons. When this ultraviolet light strikes a hydrogen atom, it can knock an electron completely free from the atom's nucleus, a process called ionization. The electron drifts through space until eventually it encounters another hydrogen nucleus and recombines with it. But in doing so, it releases energy in the form of light at very specific wavelengths. The brightest of these emission lines is called hydrogen alpha, and it produces a deep red glow. This is why so many emission nebulas appear predominantly red in color. But hydrogen is not the only element present. Oxygen, nitrogen, sulfur, and other elements also emit light when they're ionized, and then recombine with electrons. Oxygen produces a striking blue-green color. Sulfur adds additional reds. The exact color of an emission nebula depends on its composition, the temperature of the stars within it, and the density of the gas. Some regions glow almost pure red. Others show teal and blue hues where oxygen emission dominates. Still others display complex mixtures, creating some of the most beautiful and intricate structures in the universe. Emission nebulas are also called H2 regions, pronounced H2. The term refers to ionized hydrogen. Astronomers use Hi to mean neutral hydrogen with its electron intact, and H2 to mean hydrogen that's been ionized, its electron stripped away. These H2 regions are active, energetic places. They're often the sites of ongoing star formation, with new stars being born from the surrounding gas even as older stars ionize and illuminate the clouds around them. The largest and most active H2 regions can span hundreds of light years and contain hundreds or even thousands of young stars. They represent stellar nurseries on a truly colossal scale, places where the raw material of the universe is being transformed into luminous new suns that will shine for millions or billions of years. Some of the most famous nebulas in the night sky are emission nebulas. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is one of the brightest and nearest. The Lagoon Nebula in Sagittarius spans over 100 light years. The Carina Nebula in the southern sky is one of the largest known, containing some of the most massive and luminous stars in the Milky Way. Each of these clouds glows with the characteristic light of ionized gas, painting space in vivid, saturated colors. Reflection nebulas tell a different story. Unlike emission nebulas, they don't generate their own light. Instead, they shine by reflecting the light of nearby stars, much like clouds on Earth glow when illuminated by the moon. These nebulas are made primarily of dust rather than gas. The dust grains are tiny, measured in fractions of a micron, but there are countless trillions of them scattered through the cloud. When starlight strikes these dust particles, it doesn't simply pass through. Some of it is absorbed, but much of it is scattered in different directions. And here's where something interesting happens. The scattering isn't uniform across all colors. Blue light, with its shorter wavelength, scatters much more efficiently than red light. This is the same phenomenon that makes Earth's sky blue. When you look at the sky during the day, you're seeing sunlight that has scattered off molecules in the atmosphere, and the blue wavelengths scatter most strongly. In reflection nebulas, the same physics applies. The dust preferentially scatters blue light, so these nebulas often appear distinctly blue in photographs. They're like cosmic clouds illuminated from within by the blue light of stars embedded in or near them. The effect is subtle and ethereal, quite different from the vibrant reds of emission nebulas. One of the most famous reflection nebulas surrounds the Pleiades star cluster, also known as the Seven Sisters. This young cluster of bright blue stars is wrapped in faint wisps of dust that glow with reflected starlight. The nebula isn't particularly bright, requiring long exposures and dark skies to photograph, but when captured, it reveals delicate threads and filaments of blue mist around each star. Another notable example is the Trifid Nebula, which actually combines both emission and reflection components. The inner regions glow red from ionized hydrogen, while outer areas reflect blue light from nearby stars. It's divided by dark lanes of dust, giving it a three-lobed appearance that inspired its name. Reflection nebulas are often found near stellar nurseries. The dust that creates them is left over from the same molecular clouds that formed the stars. As young stars ignite and begin to shine, they illuminate the remnants of their birth clouds, creating these ghostly blue halos. Over time, stellar winds and radiation pressure from the stars will push the dust away, dispersing it back into space. The reflection nebula is temporary, a brief phase lasting perhaps only a few million years before the dust either disperses or is blown away entirely. Dark nebulas are the inverse of emission and reflection nebulas. They don't shine at all. Instead, they appear as black silhouettes against the brighter background of stars or glowing gas. These are dense clouds of dust and molecular gas, so thick and opaque that they completely block visible light from objects behind them. When you look at a dark nebula, you're not seeing emptiness. You're seeing a wall of material, a cosmic curtain drawn across the stars. Dark nebulas are cold places, among the coldest natural environments in the universe. Their temperatures typically range from 10 to 100 Kelvin, well over 200 degrees below zero on the Celsius scale. In the densest cores of these clouds, temperatures can drop even lower, approaching just a few degrees above absolute zero. At these frigid temperatures, almost all motion ceases. Atoms move sluggishly. Molecules freeze onto dust grains, forming icy coatings of water, methane, and ammonia. This coldness is essential for what happens next. In the depths of dark nebulas, gravity can overcome the thermal pressure of the gas. Regions begin to collapse slowly inward, growing denser and denser. As they do, they fragment into smaller clumps, each one a potential future star. Dark nebulas, despite their appearance as voids, are actually stellar nurseries. They're where stars form, hidden from view by the very dust that will eventually give birth to them. The largest dark nebulas can contain over 1 million times the mass of the Sun and stretch across hundreds of light years. These giants are called giant molecular clouds. They're named for the abundance of molecular hydrogen within them. In most of space, hydrogen exists as individual atoms, but in the cold, dense interiors of these clouds, atoms pair up to form H2 molecules. This molecular hydrogen makes up the bulk of the cloud's mass, though it's difficult to detect directly because it doesn't emit light at visible wavelengths. Smaller, isolated dark clouds are called Bok globules, named after the Dutch-American astronomer Bart Bok, who studied them extensively. These compact clouds are typically less than 3 light-years across and contain enough material to form perhaps 1 or 2 stars. They appear as small, round, dark spots against the Milky Way, like ink blots on a luminous canvas. Some Bok globules show signs of active star formation within them. Infrared observations can peer through the dust, revealing warm cores where protostars are beginning to heat up, preparing to ignite fusion and become true stars. One of the most famous dark nebulas is the Horsehead Nebula in Orion, part of the larger Orion molecular cloud complex. It appears as a distinctly horse-shaped silhouette, protruding into a region of glowing red gas. The Horsehead is actually just a small part of a much larger dark cloud, but its shape, sculpted by radiation from nearby stars, makes it one of the most recognizable features in the night sky. Another prominent dark nebula visible from Earth is the Coalsack Nebula, found near the Southern Cross in the southern hemisphere sky. To observers in dark locations, it appears as a conspicuous black patch in the bright band of the Milky Way, as if someone had cut a hole in the stars. In reality, it's a cloud of dust and gas about 600 light-years away, blocking the light from more distant stars. Dark nebulas remind us that the universe is not just made of light, but also of shadow. Not empty space, but material substance, cold and dense and patient, waiting in the darkness to become something new. Planetary nebulas have nothing to do with planets. The name is a historical accident, a product of early telescopes that weren't powerful enough to resolve these objects clearly. When William Herschel, the astronomer who discovered Uranus, first observed planetary nebulas through his telescope in the 1780s, they appeared as small, round, greenish disks. They reminded him of the planet Uranus, so he called them planetary nebulas. The name stuck, even though we now know they're something entirely different. A planetary nebula is the outer atmosphere of a dying star, cast off into space as a glowing shell of gas. They form when stars like our Sun, stars with masses between about 1/2 and 8 times that of the Sun, reach the end of their lives. After billions of years of steadily fusing hydrogen into helium in their cores, these stars eventually run out of fuel. Without the outward pressure of fusion to support them, they begin to collapse under their own gravity. As the core contracts, it heats up. The outer layers of the star expand dramatically, swelling to hundreds of times their original size. The star becomes a red giant, a vast, bloated sphere of cool gas with a tiny, dense core at its center. For a while, the star can fuse helium into carbon and oxygen in its core, prolonging its life. But eventually, even this fuel runs out. The core becomes too small and too cool to sustain further fusion. What happens next is both violent and beautiful. The star's outer layers, no longer gravitationally bound to the tiny core, are blown away by intense stellar winds. Sometimes this happens gradually. Other times it occurs in pulses, with material being ejected in waves over thousands of years. The result is an expanding shell of gas, moving outward at speeds of 10 to 30 kilometers per second. At the center of this expanding shell, the core of the original star remains. It's now a white dwarf, an object about the size of Earth but containing as much mass as the Sun. This gives it an incredible density, over 1 million times denser than water. A teaspoon of white dwarf material would weigh several tons on Earth. The white dwarf is extraordinarily hot, often exceeding 100,000 degrees at its surface. Though small, it's intensely luminous, especially in ultraviolet light. This ultraviolet radiation floods the expanding gas shell, ionizing it and causing it to glow. The same process that lights up emission nebulas applies here, but on a smaller, more compact scale. The nebula shines with characteristic colors, reds from hydrogen, blues and greens from oxygen, depending on the temperature of the central white dwarf and the composition of the gas. Planetary nebulas come in an astonishing variety of shapes. Some are simple rings or spheres, others are elongated cylinders or hourglasses. Still others show complex multi-lobed structures, jets or nested shells. The Ring Nebula in Lyra, Messier 57, is a perfect example of a ring-shaped planetary nebula. When viewed face-on, it appears as a smoke ring in space, a circular band of glowing gas with a dim white dwarf star at its center. The Helix Nebula, mentioned earlier as the closest planetary nebula to Earth, looks remarkably like a giant eye staring out from the cosmos. Its structure is actually a cylinder or tunnel of gas that we happen to be viewing almost directly down its axis, creating the illusion of a flat disk. If we could view it from the side, it would appear elongated, more like a stretched out cylinder than a ring. The Eskimo Nebula, the Cat's Eye Nebula, the Butterfly Nebula, each has earned descriptive names based on their appearance. The Cat's Eye is particularly complex, showing multiple concentric rings, nested shells, and intricate filaments that suggest a turbulent, multi-stage ejection process. The Butterfly Nebula, also called NGC 6302, has vast wings of gas extending to either side of a central star, resembling a cosmic insect frozen in mid-flight. Scientists are still working to understand what causes these varied morphologies. Some shapes may be influenced by binary companion stars, where a second star's gravity distorts the material being ejected. Others might be shaped by magnetic fields threading through the gas. or by rotation of the central star. The complexity suggests that the deaths of stars, even relatively simple stars like the Sun, are far more intricate than we once thought. Planetary nebulas are not permanent. As the gas expands outward, it grows more diffuse. The shell spreads into the surrounding interstellar medium, eventually becoming too thin to detect. Most planetary nebulas last only 10 to 20,000 years before they fade into invisibility. That's a mere blink on cosmic timescales, which is why we don't see vast numbers of them in the sky, despite the fact that stars are dying all the time. But during their brief existence, planetary nebulas play a crucial role in galactic ecology. The gas they return to space is enriched with heavier elements, atoms that were created through fusion in the star's core. Carbon, nitrogen, oxygen, and other elements forged in the stellar furnace are released back into the interstellar medium, where they can eventually be incorporated into new stars and planets. The oxygen you're breathing right now, the carbon in your body, much of it was created inside dying stars and released through planetary nebulas billions of years ago. Our own sun will create a planetary nebula someday. In about 5 billion years, it will exhaust its hydrogen fuel and begin to swell into a red giant. The inner planets, including Earth, will likely be engulfed as the sun's outer layers expand to roughly the orbit of Mars. Then, over the course of a few 100,000 years, the sun will shed those layers into space, creating a faint shell of glowing gas around a white dwarf core. Long after humanity is gone, long after Earth itself has been consumed, the sun will leave behind this beautiful, ghostly monument to its existence. Supernova remnants represent the most violent form of nebula. These are the shredded remains of massive stars that have exploded in supernovas, one of the most energetic events in the universe. When a star significantly more massive than the Sun reaches the end of its life, it doesn't go gently like smaller stars do. Its death is catastrophic. Massive stars burn through their fuel much faster than smaller stars. While the Sun will live for about 10 billion years, a star 20 times more massive might last only 10 million years. It races through its life in a cosmic sprint, fusing hydrogen into helium, then helium into carbon and oxygen, then those elements into neon, magnesium, silicon, and eventually iron. Each stage of fusion releases less energy than the previous one, and each stage burns for a shorter time. When the core becomes iron, the star faces a crisis. Iron cannot be fused to release energy. Fusing iron actually consumes energy rather than producing it. The core, now made of iron, suddenly loses its source of pressure support. In less than a second, it collapses catastrophically. The core, which might have been about the size of Earth, compresses down to a sphere only 20 kilometers across. The outer layers of the star, suddenly unsupported, fall inward at a significant fraction of the speed of light. This implosion creates unimaginable pressures and temperatures. The infalling material rebounds off the ultra-dense core, creating a shock wave that tears through the star's outer layers. The shock heats the gas to billions of degrees, triggering a thermonuclear explosion that rips the star apart. For a few weeks, the supernova can shine as brightly as an entire galaxy, outshining billions of normal stars. The debris from this explosion expands outward at tremendous speeds, typically 10 to 30,000 kilometers per second, about 3 to 10% the speed of light. This material plows into the surrounding interstellar medium like a cosmic snowplow, sweeping up and compressing the gas and dust it encounters. The collision creates shock fronts that heat the material to millions of degrees, causing it to emit X-rays and other high-energy radiation. The result is a supernova remnant, expanding shell of hot, glowing gas and shocked interstellar material. These remnants can be enormous, spanning tens or even hundreds of light years across, and they glow not just from their own heat, but also through the same ionization processes that light up emission nebulas as the shockwaves energize the surrounding gas. The most famous supernova remnant is the Crab Nebula, the debris from a supernova that exploded in the year 1054. Chinese astronomers recorded the appearance of a guest star in the constellation Taurus, so bright it was visible during the day for several weeks. That guest star was the supernova. Today, nearly 1,000 years later, the debris has expanded into a complex filamentary nebula about 11 light-years across. At the heart of the Crab Nebula lies a pulsar, a rapidly spinning neutron star that flashes 30 times per second. This pulsar is the collapsed core of the original star, now compressed to an object about 20 kilometers in diameter, but containing more mass than the Sun. It spins incredibly fast, and its powerful magnetic field sweeps around with it, like a cosmic lighthouse beam. This rotation creates jets and rings of high-energy particles that light up the interior of the nebula with a strange blue glow. Other famous supernova remnants include the Veil Nebula in Cygnus, a delicate lacework of glowing filaments from an explosion that occurred thousands of years ago. The Cassiopeia A remnant is younger, only about 350 years old, though the explosion itself was apparently missed by observers on Earth, possibly because intervening dust made it too faint to see. And the remnant of Kepler's supernova, observed in 1604, remains visible today as a faint shell expanding in the constellation Ophiuchus. Supernova remnants are crucial to the galaxy's ecosystem. They inject enormous amounts of energy into the interstellar medium, stirring and heating it. The shockwaves can trigger the collapse of nearby molecular clouds, initiating new rounds of star formation. And perhaps most importantly, supernovas are responsible for creating and dispersing most of the heavy elements in the universe. Elements heavier than iron cannot be created through normal fusion in stellar cores. They require the extreme conditions of a supernova explosion, where temperatures and pressures briefly reach levels high enough to forge atoms of gold, platinum, uranium, and other heavy elements. Every atom of gold in your jewelry, every atom of iron in your blood, was created in a supernova explosion billions of years ago and scattered into space, eventually finding its way into the cloud from which our solar system formed. Without supernovas, the universe would be a very different place. Planets like Earth, which depend on heavy elements for their rocky composition and complex chemistry, could not exist. Life, which requires carbon, oxygen, nitrogen, and many other elements, would be impossible. We are, quite literally, made of stardust, the ashes of ancient supernovas mixed into the material that became the Sun, Earth, and ultimately us. Nebulas paint the universe in colors, and each color tells a story, written in the language of physics and chemistry. When you see a photograph of a nebula, those striking reds, blues, greens, and purples aren't arbitrary or artificially colored for aesthetic effect. They represent real physical processes, emissions of light at specific wavelengths corresponding to the elements present, and the conditions within the nebula. The most common color in nebulas is red, produced by hydrogen alpha emission. Hydrogen is by far the most abundant element in the universe, making up about 90% of all atoms. When hydrogen atoms are ionized by ultraviolet light from nearby stars, and then recombine with electrons, they emit light at very specific wavelengths. The brightest of these is the hydrogen alpha line at 656.3 nanometers, deep in the red part of the visible spectrum. This red glow dominates many emission nebulas: the Orion Nebula, the Lagoon Nebula, the Rosette Nebula. All show this characteristic red color in long exposure photographs. It's the signature of hydrogen being energized and then releasing that energy as red photons. Interestingly, hydrogen also emits at other wavelengths. Hydrogen beta produces blue cyan light. Hydrogen gamma adds violet. But hydrogen alpha is typically the strongest line, so red tends to dominate unless other elements contribute significantly to the nebula's light. Oxygen produces a very different color. When oxygen is doubly ionized, meaning 2 of its electrons have been stripped away, it can emit light at 507 nanometers, right in the blue-green part of the spectrum. This emission line, called O3, often appears as teal or turquoise in nebula photographs. It requires higher energy to produce than hydrogen alpha, so O3 emission typically indicates regions where the ultraviolet radiation from stars is particularly intense, capable of stripping multiple electrons from atoms. The center of the Orion Nebula shows this oxygen emission. The trapezium cluster at its heart contains several extremely hot, massive stars that flood the surrounding gas with energetic ultraviolet photons. This creates a region rich in O3 emission, adding shades of teal and blue to the overall red glow. The contrast between the red hydrogen-rich outer regions and the blue-green oxygen-rich core gives the nebula its characteristic multicolored appearance. Sulfur adds yet another shade to the palette. Sulfur-2 emission produces wavelengths at 671 and 673 nanometers, slightly redder than hydrogen alpha. In regions where sulfur is abundant and ionized, it contributes additional red and orange tones. Professional astrophotographers often take separate images through filters designed to isolate hydrogen alpha, O3 and S2 emissions, then combine them to create stunning false color images that reveal the distribution of these elements throughout the nebula. The exact color of a nebula also depends on how much dust is present. Dust doesn't just reflect and scatter light. It also absorbs it, particularly at shorter wavelengths. Blue light is absorbed more readily than red light. This means that in regions with significant dust, the blue and green emissions may be dimmed or blocked entirely, allowing the red tones to dominate even more strongly. This reddening effect is similar to why the sun appears orange or red at sunset. The sunlight has to pass through more of Earth's atmosphere, which scatters away the blue light, leaving primarily the red and orange wavelengths to reach our eyes. In reflection, nebulas, the color comes from scattering rather than emission. The tiny dust grains scatter blue light more efficiently than red light, giving these nebulas their characteristic blue hue. It's the same Rayleigh scattering that makes Earth's sky blue during the day. The shorter wavelength blue photons bounce off dust particles in all directions, while longer wavelength red photons tend to pass straight through or be absorbed. The result is a blue glow surrounding the stars that illuminate the dust. Some nebulas show both emission and reflection components. The Trifid Nebula, for example, has a red emission nebula at its center where ionized hydrogen glows, surrounded by blue reflection nebulosity where starlight scatters off nearby dust. The juxtaposition of red and blue in a single object creates a striking visual contrast. Red for the hot, ionized gas, and blue for the cool, reflecting dust. Dark nebulas, of course, show no color at all. They absorb light rather than emitting or reflecting it, appearing as black silhouettes. But even here, color plays a role. When dust absorbs light, it doesn't do so uniformly across all wavelengths. Blue light is absorbed more than red light. This selective absorption is part of why dark nebulas appear so dark. They're incredibly efficient at blocking the blue and ultraviolet light from background stars, though some red light can still leak through the densest cores if observed at infrared wavelengths. The colors of nebulas aren't just beautiful. They're diagnostic tools that allow astronomers to determine the composition, temperature, density, and ionization state of these clouds. By analyzing the specific wavelengths of light a nebula emits, scientists can measure how much hydrogen, oxygen, nitrogen, sulfur, and other elements are present. They can determine how hot the gas is, how dense it is, and how intensely it's being irradiated by nearby stars. Each color is a clue, a piece of information encoded in the light that has traveled across space to reach us. Nebulas are not just beautiful clouds drifting through space. They're also the birthplaces of stars. Within their cold, dense interiors, gravity performs its patient work, gathering material together over millions of years until new suns ignite and begin to shine. Star formation begins in molecular clouds, those vast accumulations of gas and dust we discussed earlier. These clouds are gravitationally bound, meaning their own gravity holds them together despite the internal pressure of the gas. But for stars to form, something has to push the cloud beyond a critical threshold, making it dense enough that gravity can overcome the gas pressure and trigger collapse. Sometimes this trigger comes from external events. A nearby supernova's shockwave can compress a molecular cloud, creating regions dense enough to collapse. The spiral arms of the galaxy can also compress clouds as they pass through them, like traffic bunching up on a highway. Collisions between clouds can provide the needed compression. Even the radiation pressure from nearby massive stars can sculpt and compress the edges of clouds, creating dense clumps. Once a region becomes dense enough, it begins to collapse under its own gravity. But it doesn't collapse uniformly. The cloud fragments into many smaller clumps, each one destined to become an individual star or star system. As each clump collapses, it heats up. Gravitational potential energy converts into thermal energy. The center of the collapsing region grows hotter and denser. Eventually, the core of the collapsing clump becomes so hot and dense that hydrogen nuclei can overcome their mutual electrical repulsion and fuse together, forming helium and releasing energy. Nuclear fusion ignites. A star is born. This process takes time, anywhere from 100,000 years for massive stars to tens of millions of years for small, low-mass stars like red dwarfs. The newborn star emerges still embedded in its birth cloud, surrounded by dust and gas. Its light and stellar wind begin to clear away this material, carving out a cavity. If the star is massive and hot, its ultraviolet radiation will ionize the surrounding gas, creating an emission nebula around itself. Over time, the radiation pressure and stellar winds from multiple young stars can blow away the entire molecular cloud, dispersing it back into the interstellar medium. Some of the most spectacular images of nebulas show this process in action. The pillars of creation in the Eagle Nebula are towering columns of gas and dust, each several light years tall, where active star formation is occurring. At the tips of these pillars, dense knots of material are collapsing to form new stars. But even as these stars are being born, they're also destroying their environment. The intense ultraviolet light from nearby massive stars is eroding the pillars, causing them to evaporate slowly from their surfaces. The pillars appear dark and opaque in visible light because they're made of cold, dense dust that blocks starlight. But infrared observations can peer through this dust, revealing the infant stars hidden within. These protostars haven't yet fully ignited fusion. They're still in the process of collapsing and heating up. Some are surrounded by accretion disks, spinning rings of material that will eventually form planets. The Eagle Nebula itself is a massive region of active star formation, containing thousands of young stars at various stages of development. At its heart lies an open cluster of hot, massive stars that provide the energy to light up the surrounding gas. The nebula spans over 70 light-years and lies about 7,000 light-years from Earth. It's a stellar nursery on a grand scale, a place where the next generation of stars is being born from the ashes of previous stellar cycles. The Orion Nebula is another extraordinary stellar nursery, the closest and brightest region of massive star formation to Earth. Located only about 1,300 light-years away, it's visible to the naked eye as the middle star in Orion's sword. Through a telescope, it resolves into a glowing cloud of gas surrounding a cluster of young stars called the trapezium. The trapezium contains 4 bright stars easily visible in small telescopes, along with several fainter companions. These stars are incredibly young, only about 1 million years old. They're also extremely hot and massive. Their ultraviolet radiation ionizes the surrounding nebula, creating the characteristic red and teal glow. But the trapezium stars are just the tip of the iceberg. Infrared observations reveal thousands of additional young stars and protostars embedded in the cloud, most of them too faint or too obscured by dust to see at visible wavelengths. Many of these young stars are surrounded by protoplanetary disks, also called proplyds. These disks are made of dust and gas left over from star formation, the raw material from which planets will eventually coalesce. Hubble's Space Telescope images of the Orion Nebula show hundreds of these disks in silhouette against the bright background nebula. They appear as dark, teardrop-shaped structures with the young star at their centers. The disks are being evaporated by the intense radiation from the trapezium stars, creating tails of material streaming away like cosmic tadpoles. The Orion Nebula is actually just the visible face of a much larger structure called the Orion Molecular Cloud Complex. This vast region spans hundreds of light-years and contains enough gas to form hundreds of thousands of stars. Most of it is invisible at optical wavelengths, hidden behind opaque dust clouds. But it's one of the most active and important star-forming regions in our part of the galaxy. The Carina Nebula, visible in the southern sky, is even larger and more active than Orion. It contains some of the most massive and luminous stars known, including Eta Carinae, a hypergiant star more than 100 times the mass of the Sun. Eta Carinae is so massive and so bright that it's unstable, periodically erupting and shedding material. In the 1800s, it underwent a massive outburst, briefly becoming one of the brightest stars in the sky despite being thousands of light-years away. The Carina Nebula hosts multiple clusters of young stars, vast pillars of gas and dust, and regions of intense ionization. It's a chaotic, violent place where stellar birth and stellar death occur side by side. Massive stars born only a few million years ago are already nearing the end of their lives, soon to explode as supernovas and send shockwaves through the nebula, potentially triggering new rounds of star formation. These stellar nurseries show us that stars don't form in isolation. They're born in clusters and associations, groups of stars that all emerge from the same molecular cloud at roughly the same time. Our own Sun was likely born in such a cluster, though its siblings have long since drifted apart, scattered across the galaxy by gravitational interactions over the past 4.5 billion years. Star formation is not just an ancient process, it's ongoing, happening right now in countless nebulas throughout the Milky Way and in other galaxies. Every year, the galaxy produces a few new solar masses worth of stars. That might not sound like much, but over millions and billions of years, it adds up to a significant fraction of the galaxy's stellar population. The nebulas we see today are factories of creation, churning out new stars that will light the universe for eons to come. Certain nebulas have become famous, not just among astronomers but in popular culture. Their images have been reproduced countless times, adorning posters, book covers, and computer screens. Each has its own unique character, its own story to tell. The Orion Nebula is perhaps the most famous, visible to the naked eye and easily observed through even small telescopes. It's been known since ancient times, though early observers didn't understand what they were seeing. To the unaided eye, it appears as a fuzzy star in the middle of Orion's sword, hanging below the 3 stars of the belt. Through a telescope, it resolves into a magnificent cloud of glowing gas and dust, one of the most photographed objects in the night sky. What makes the Orion Nebula so special is its combination of proximity and activity. At only 1,300 light-years away, it's close enough that we can study it in extraordinary detail. And it's active enough to provide a window into many different stages of stellar birth. From protostars still embedded in their dusty cocoons to young stars already blowing away their birth clouds, the Orion Nebula showcases the full spectrum of star formation. The Crab Nebula holds a different kind of fame. It's the remnant of a supernova observed and recorded by astronomers in 1054. Today it appears as a chaotic tangle of filaments expanding outward from a central pulsar. The nebula's structure is incredibly complex, with fast-moving jets, shock fronts, and a strange blue glow from high-energy particles accelerated by the pulsar's magnetic field. The Crab Nebula is still expanding today, growing by about 1,500 kilometers every second. If you could watch it over the course of years, you'd actually see it visibly change size. Astronomers have compared photographs taken decades apart and measured this expansion, using it to calculate when the explosion occurred and confirming the link to the supernova of 1054. The Eagle Nebula owes much of its fame to a single image, the Pillars of Creation photograph taken by the Hubble Space Telescope in 1995. That image became one of the most iconic space photographs ever captured, showing 3 towering columns of gas and dust rising from a sea of glowing nebulosity. The pillars are backlit by the glow of the nebula, creating a dramatic silhouette effect. The image resonated with people not just because it was beautiful, but because it showed something profound. Those pillars are stellar nurseries, places where new stars are being born even as we watch. The photo captured creation itself, frozen in a moment of cosmic time. It's been reproduced countless times, becoming almost synonymous with deep space imagery. Subsequent observations by other telescopes have added to our understanding of the Eagle Nebula. Infrared images from the James Webb Space Telescope pierce through the dust, revealing the infant stars hidden within the pillars. X-ray observations show the hot, energetic environments around the young stars. Each wavelength tells part of the story, and together they paint a complete picture of a stellar nursery at work. The Horsehead Nebula is another icon, instantly recognizable by its distinctive shape. It's a dark nebula silhouetted against the bright emission nebula IC 434. The horsehead shape is actually just a chance alignment, a projection effect caused by our viewing angle. If we could see it from a different perspective, it would likely look quite different. The Horsehead is located in the Orion Molecular Cloud Complex, relatively close to the Orion Nebula itself, though appearing in a different part of the sky. It's illuminated from behind by the bright star Sigma Orionis, which ionizes the background nebula and creates the red glow against which the Horsehead stands out. The dark cloud that forms the Horsehead is cold and dense, a region where stars may be forming in the hidden depths. Interestingly, the Horsehead Nebula is doomed. The same radiation that illuminates it from behind is also slowly eroding it. Like a sand sculpture being worn away by wind, the Horsehead is gradually being evaporated by the intense starlight. Astronomers estimate that in about 5 million years, it will be gone, its distinctive shape lost forever. It's a reminder that nebulas, for all their apparent solidity, are temporary structures slowly changing and evolving over cosmic time. The Helix Nebula is often called the Eye of God, due to its eerie resemblance to a giant eye staring out from space. It's a planetary nebula, the shed outer layers of a sun-like star that reached the end of its life. Located only about 650 light-years from Earth, it's the closest planetary nebula to us, and subtends a large angular size in the sky, about half the diameter of the full moon. Despite its size, the helix is quite faint, because its light is spread out over such a large area. To see it well requires a dark sky and either binoculars or a telescope. Long exposure photographs reveal its intricate structure, concentric rings of glowing gas with a white dwarf star at the center. The nebula is actually a cylinder viewed end-on, giving it the illusion of being flat. Within the Helix Nebula, astronomers have identified thousands of comet-like knots, small, dense clumps of gas, each about twice the size of our solar system. These knots have tails pointing away from the central star, sculpted by the stellar wind and radiation. Their origin is somewhat mysterious, possibly formed during the initial ejection of material or perhaps shaped by later interactions. The Lagoon Nebula, also known as Messier 8, is a massive emission nebula in Sagittarius. It spans over 100 light-years and lies about 5,000 light-years from Earth. The nebula is bisected by a dark lane of dust, which gives it its lagoon-like appearance and inspired its name. Within the bright regions, active star formation is occurring, creating new generations of stars from the surrounding gas. The Lagoon Nebula is visible to the naked eye from dark locations, appearing as a faint, misty patch in the Milky Way. Through binoculars or a telescope, it reveals beautiful structure with bright knots of emission nebulosity, dark dust lanes, and an open cluster of young stars. Long exposure photographs bring out its full glory, showing delicate filaments, shock fronts, and regions where new stars are being born. The Carina Nebula in the southern sky is one of the largest and brightest nebulas known. It contains the massive star Eta Carinae along with numerous other hot young stars. The nebula is a chaotic region of star formation, with vast pillars of gas, expanding bubbles, and complex shock structures. Infrared observations reveal thousands of young stars embedded in the clouds, many of them still surrounded by protoplanetary disks. The Carina Nebula is only visible from southern latitudes, which made it less well known historically than northern nebulas like Orion. But with modern imaging technology and increased study, it has gained recognition as one of the most important star-forming regions in the galaxy. The sheer number of massive stars within it, combined with its relative proximity of about 7,000 light-years, make it an invaluable laboratory for studying stellar birth and evolution. Each of these famous nebulas tells us something about the universe, about how matter organizes itself, how stars form and die, how elements are created and dispersed. They're not just pretty pictures. They're windows into cosmic processes that shape galaxies and seed the universe with the raw materials for planets and life. We've already discussed planetary nebulas in the context of different nebula types, but they deserve a deeper exploration. These structures represent one of the final acts in the life cycle of stars like our Sun, and they offer profound insights into stellar evolution and the enrichment of the interstellar medium. When a star between about 1/2 and 8 solar masses exhausts its nuclear fuel, it faces an inevitable transformation. The core contracts into a white dwarf while the outer envelope is expelled into space. But this process doesn't happen instantaneously. It unfolds over tens of thousands of years, and the details determine the final appearance of the planetary nebula. Some planetary nebulas are nearly perfect spheres, suggesting a relatively symmetric ejection of material. Others show pronounced bipolar structure, with 2 lobes of gas extending in opposite directions from the central star. Still others display multiple nested shells, indicating several distinct episodes of mass loss. The variety suggests that the process of creating a planetary nebula is complex and influenced by factors we're still working to understand. One possibility is that many planetary nebulas result from binary star systems. If the dying star has a companion, the gravitational interaction between them can funnel material into specific directions, creating asymmetric outflows. The companion might even accrete material from the expanding envelope, growing larger while the primary star shrinks to a white dwarf. Some planetary nebulas show direct evidence of companion stars, though in many cases the companion is too faint to detect. Rotation also plays a role. A spinning star will preferentially eject material along its equator, creating a disk or torus of gas around its midsection, while material flows out more freely along the poles. This can produce the classic hourglass or bipolar shapes seen in many planetary nebulas. The faster the star spins, the more pronounced the effect. Magnetic fields may also shape planetary nebulas. As the star sheds its outer layers, the magnetic field lines can channel material into specific patterns, creating jets and collimated outflows. The interaction between the magnetic field, rotation, and stellar winds creates a complex interplay that produces the diverse morphologies we observe. At the center of each planetary nebula is the white dwarf, the exposed core of the original star. This remnant is incredibly hot immediately after formation, often exceeding 100,000 Kelvin. Over time it cools, but this cooling is extremely slow. A white dwarf will take billions of years to cool enough to stop emitting visible light. White dwarfs are supported not by fusion or gas pressure, but by electron degeneracy pressure. This is a quantum mechanical effect that prevents electrons from being squeezed too closely together. When matter becomes incredibly dense, electrons are forced into higher and higher energy states according to the Pauli exclusion principle. This creates an outward pressure that can support the star against gravitational collapse, at least up to a certain mass limit. That limit, called the Chandrasekhar limit, is about 1.4 solar masses. If a white dwarf somehow accretes enough material to exceed this mass, electron degeneracy pressure can no longer support it. The star undergoes catastrophic collapse, triggering a thermonuclear explosion called a Type Ia supernova. These explosions are so violent that they completely destroy the star, leaving no remnant behind, only an expanding cloud of debris. The white dwarf at the center of a planetary nebula illuminates the surrounding gas with ultraviolet radiation. This radiation ionizes the atoms in the nebula, causing them to emit the characteristic glow we see. As the white dwarf cools over thousands of years, it emits less ultraviolet light. Eventually it becomes too cool to ionize the gas effectively, and the planetary nebula fades from view. But even after the nebula has dispersed, the white dwarf remains. It will continue cooling for billions or even trillions of years, gradually fading from white to yellow to red, to eventually a theoretical black dwarf, a cold, dark cinder of a star that no longer emits any light. However, the universe is not yet old enough for any black dwarfs to have formed. The oldest white dwarfs are still glowing faintly, remnants of stars that died when the universe was young. Planetary nebulas contribute significantly to the chemical enrichment of galaxies. The gas they return to space contains elements created through fusion in the star's core. Carbon, nitrogen, and oxygen, essential elements for life, are produced in abundance in sun like stars and released through planetary nebulas. Over billions of years, countless generations of stars have created planetary nebulas, gradually increasing the metallicity of the galaxy. This enrichment is cumulative. The first generation of stars, born from the primordial hydrogen and helium left over from the Big Bang, could produce only limited amounts of heavy elements. But when these stars died and created planetary nebulas or exploded as supernovas, they seeded the interstellar medium with carbon, oxygen, and other elements. The next generation of stars formed from gas that was slightly enriched, and they in turn created even more heavy elements when they died. Each stellar generation builds on the previous one, slowly transforming the galaxy from a pure mixture of hydrogen and helium into a more complex chemical environment. This process makes planets like Earth possible, and ultimately makes life possible. We exist because countless stars before the sun lived and died, creating and dispersing the elements that now make up our world and our bodies. Our sun's fate is to become a planetary nebula. In about 5 billion years, it will exhaust the hydrogen in its core and begin to swell into a red giant. The inner planets will likely be consumed. Then, over the course of hundreds of thousands of years, the sun will shed its outer layers in pulses, creating an expanding shell of gas. At the center will remain a white dwarf, a stellar remnant about the size of Earth but containing most of the sun's current mass. The planetary nebula our sun creates will probably be similar to the helix or the ring nebula, a roughly circular shell of glowing gas. It will shine for perhaps 20,000 years before fading into invisibility, and the white dwarf will cool slowly over countless billions of years, eventually becoming a cold, dark remnant, a monument to the star that once warmed our world and made life possible. Supernova remnants are the most violent and energetic type of nebula, born from explosions that can briefly outshine entire galaxies. We've touched on them before, but their importance to galactic ecology warrants deeper examination. When a massive star explodes as a supernova, it releases more energy in a few seconds than the sun will emit over its entire 10 billion year lifetime. Most of this energy is carried away by neutrinos, ghostly particles that barely interact with matter and escape directly into space. But enough energy remains in the form of kinetic energy and heat to create an expanding shockwave that propagates through space at thousands of kilometers per second. This shockwave is not a single smooth surface. It's actually composed of multiple layers. The outermost layer is called the forward shock or blast wave. This is where the ejected stellar material slams into the surrounding interstellar medium, heating it to millions of degrees and creating a bright shell visible in X-rays and other wavelengths. Behind the forward shock is the reverse shock, formed as the high-pressure region behind the blast wave pushes back on the stellar ejector. This reverse shock heats the ejector itself, causing it to emit radiation. Between the forward and reverse shocks is a region of compressed, shocked interstellar material mixed with hot ejecta. The structure of a supernova remnant evolves over time. Initially, in what's called the free expansion phase, the ejected material simply flies outward at a constant velocity, determined by the energy of the explosion. The shock wave is driven primarily by the momentum of the ejecta. This phase lasts for a few hundred to a few thousand years, depending on the energy of the explosion and the density of the surrounding medium. Eventually, the shock wave sweeps up enough interstellar material that its mass becomes comparable to the mass of the ejecta. At this point, the remnant enters the Sedov-Taylor phase, named after the physicists who first described it. The shock wave begins to slow down as it plows through more and more material. The remnant's expansion becomes driven more by pressure than by simple momentum. During this phase, which can last tens of thousands of years, the supernova remnant is at its brightest and most visually impressive. The shock-heated gas glows intensely across the electromagnetic spectrum. Young remnants like Cassiopeia A and the Crab Nebula are in this phase. They show complex filamentary structures, bright shells, and intricate details that reveal the physics of shock waves and plasma dynamics. After many tens of thousands of years, the shock wave slows to the point where it can no longer heat the gas to X-ray emitting temperatures. The remnant enters the radiative phase. The gas begins to cool, losing energy through radiation faster than the shock can heat it. The bright shell breaks up into filaments and fragments as instabilities develop. The remnant gradually merges with the background interstellar medium, becoming indistinguishable from ordinary gas clouds. Eventually, after hundreds of thousands or even millions of years, the supernova remnant fades completely. The ejected material has fully mixed with the surrounding medium, enriching it with the heavy elements created in the explosion. The energy of the shock wave has been dissipated. All that remains is a diffuse cloud of slightly enriched gas, perhaps a neutron star or black hole at the center marking the grave of the original star. Supernova remnants play a crucial role in shaping the interstellar medium. The shock waves they produce stir and heat the gas, creating a complex structure of hot and cold regions, compressed shells and evacuated bubbles. This turbulence affects how the interstellar medium behaves, influencing where and when new stars can form. The heavy elements released by supernovas enrich the interstellar medium, raising its metallicity. Elements like carbon, oxygen, silicon, and iron, created through fusion in massive stars and through the supernova explosion itself, are mixed into the gas. When new stars form from this enriched material, they and their potential planets contain these heavy elements from the start. Supernova remnants are also thought to be a major source of cosmic rays, high-energy particles that zip through space at nearly the speed of light. The shock waves in supernova remnants can accelerate charged particles to enormous energies through a process called diffusive shock acceleration. Particles bounce back and forth across the shock front, gaining energy with each crossing. Some particles reach energies millions or billions of times higher than their rest mass energy, becoming cosmic rays. These cosmic rays permeate the galaxy, constantly bombarding everything, including Earth. They contribute to the background radiation in space, present a hazard to astronauts, and even influence chemical reactions in the interstellar medium. Some scientists have suggested that cosmic ray impacts on Earth's atmosphere may influence cloud formation and climate patterns, though this remains a topic of active research. At the center of many supernova remnants lies the collapsed core of the original star, either a neutron star or a black hole. Neutron stars are extraordinarily dense objects, containing more mass than the Sun compressed into a sphere only about 20 kilometers across. A teaspoon of neutron star material would weigh about 1 billion tons. Some neutron stars are pulsars, rapidly rotating and beaming radio waves from their magnetic poles like cosmic lighthouses. The Crab Nebula's pulsar spins 30 times per second, and its powerful magnetic field drives a wind of high-energy particles that light up the interior of the nebula with a strange blue glow quite different from the red emission of hydrogen-rich nebulas. Other neutron stars are magnetars possessing magnetic fields 1,000 trillion times stronger than Earth's. These fields are so intense they warp the vacuum of space itself, creating exotic quantum effects. Occasionally, magnetars undergo starquakes, sudden rearrangements of their crusts that release enormous bursts of X-rays and gamma rays. If the original star was massive enough, its core may collapse beyond even the neutron star stage, becoming a black hole. These objects are so dense that their escape velocity exceeds the speed of light. Nothing, not even light itself, can escape from within the event horizon. Black holes at the centers of supernova remnants are difficult to detect directly, but their presence can be inferred from X-ray emissions as material falls toward them and heats up. Supernova remnants connect stellar death to stellar birth. They enrich the interstellar medium with heavy elements. They trigger the collapse of nearby molecular clouds through their shock waves. They heat and stir the gas, creating the complex, turbulent environment from which the next generation of stars will emerge. In this way, death gives rise to new life, and the cycle continues, endlessly renewing the galaxy's stellar population. Dark nebulas, though they don't emit or reflect light, are among the most important objects in the galaxy. They're the coldest, densest regions of the interstellar medium, and they're where most stars are born. We've already discussed the basic properties of dark nebulas, their coldness, their opacity, their role as stellar nurseries. But it's worth emphasizing just how extreme the conditions inside these clouds can be. Temperatures of 10 or 20 Kelvin, barely above absolute zero. Densities that, while still incredibly sparse by terrestrial standards, are hundreds or thousands of times higher than the average interstellar medium. An almost complete absence of light, with only the faintest infrared glow from embedded protostars penetrating the darkness. These conditions allow molecules to form. In most of space, ultraviolet light from stars breaks apart molecules almost as quickly as they form. But deep inside dark nebulas shielded by countless layers of dust, molecules can survive. Hydrogen atoms pair up to form H2. Carbon and oxygen combine to form carbon monoxide. More complex molecules form on the surfaces of dust grains, where atoms and simple molecules stick and react to create compounds like water, methane, ammonia, and even amino acids. Dark nebulas are thus not just hydrogen and helium. They're chemically rich environments containing dozens or even hundreds of different molecular species. Radio telescopes tuned to specific frequencies can detect the emission lines of these molecules, mapping out their distribution within the clouds. Each molecule has its own characteristic temperature and density range, so by studying which molecules are present and where, astronomers can reconstruct the physical conditions throughout the nebula. The structure of dark nebulas is hierarchical and complex. At the largest scale, giant molecular clouds span hundreds of light years and contain hundreds of thousands or even millions of solar masses of material. These giants are subdivided into smaller clumps, which in turn contain even smaller, denser cores. It's in these cores, regions only a fraction of a light year across, that stars actually form. The cores are kept cold by the very dust that makes them opaque. When a dust grain absorbs a photon, it heats up slightly, but it then re-radiates that energy at longer wavelengths, infrared rather than visible light. This infrared radiation can escape from the cloud more easily than visible light, carrying away heat. The result is that the interiors of dark nebulas are refrigerated, kept cold by the continuous absorption and re-emission of radiation by dust grains. This coldness is crucial for star formation. If the gas were warm, its thermal pressure would prevent collapse. But at 10 or 20 Kelvin, the thermal pressure is very low. Gravity can dominate, pulling material inward. As the core collapses, it heats up slightly due to compression. But as long as the heat can be radiated away efficiently, the collapse continues. Eventually, the center of the collapsing core becomes opaque, even to infrared light. At this point, heat can no longer escape efficiently. The temperature begins to rise rapidly. The rising temperature increases the gas pressure, which begins to slow the collapse. The object has become a protostar, a hot core at the center of an infalling envelope of gas and dust. The protostar continues to grow as more material falls onto it. Jets of gas are often expelled along the rotation axis, carrying away excess angular momentum and allowing the infall to continue. Surrounding the protostar is an accretion disk, a flattened rotating disk of material that gradually spirals inward, feeding the growing star. This stage lasts for several 100,000 to several million years depending on the mass of the forming star. Small stars take longer to form. Massive stars form more quickly but begin affecting their environment sooner, as their intense radiation pressure and stellar winds begin to disrupt the surrounding cloud. When the core temperature reaches about 10 million Kelvin, hydrogen fusion ignites. The protostar becomes a true star, generating its own energy through nuclear reactions. The infall of material stops as the radiation pressure from the new star clears away the remaining envelope. What's left is a young star, perhaps still surrounded by a protoplanetary disk, from which planets will eventually form. Dark nebulas contain many such protostars and young stars at various stages of this process. Infrared observations can identify them, warm spots in the cold clouds where star formation is actively occurring. Some dark nebulas are relatively quiescent, with only a few protostars scattered through them. Others are actively forming dozens or hundreds of stars simultaneously. Barnard 68, a well-studied Bok globule, is a perfect example. It's a small, dense, isolated dark cloud about half a light year across, containing roughly twice the mass of the Sun. At visible wavelengths, it appears as a nearly perfect circular black spot against the background stars. But infrared observations reveal its temperature structure and density distribution, showing that it's on the verge of collapse. It may already contain one or more embedded protostars, though they're too obscured to detect directly yet. Over the next few 100,000 years, Barnard 68 will likely collapse to form one or perhaps two stars. The process will be hidden from view, buried deep within the dusty cloud. Only when the new stars begin to emit enough light and wind to blow away the surrounding material will they emerge into visibility. By then, the dark nebula will have been transformed, its material either incorporated into the new stars and their planetary systems or dispersed back into the interstellar medium. Dark nebulas are transient structures. Star formation destroys them. The very process they enable leads to their own demise. Young stars ionize and heat the gas, dispersing it. Stellar winds blow it away. Supernovas from the most massive stars can completely disrupt a cloud, scattering it across parsecs. Within a few tens of millions of years, a region of active star formation will have exhausted its available gas and dust, leaving behind only a scattered association of young stars where once there was a dark nebula. But the process is cyclical. The dispersed material doesn't vanish. It mixes with the interstellar medium, perhaps enriched by heavy elements from supernovas. Eventually, gravitational perturbations or shock waves from other events will cause it to recondense. New molecular clouds will form, new dark nebulas will appear, and the cycle of stellar birth and death will continue, perpetually renewing the galaxy's population of stars. Nebulas are governed by physical laws, the same laws that operate everywhere in the universe. Understanding the physics and chemistry within these clouds reveals how matter organizes itself, how energy flows, and how the raw materials of the cosmos are transformed into stars and planets. The primary force shaping nebulas is gravity. It pulls matter together, creating the density variations that lead to cloud formation and eventual star birth. But gravity doesn't act alone. It competes with pressure, the outward push of hot gas resisting compression. The balance between gravity and pressure determines whether a cloud will collapse to form stars or remain stable. In most of the interstellar medium, pressure dominates. The gas is too hot and too diffuse for gravity to overcome the thermal pressure. But in molecular clouds, where temperatures drop to 10 or 20 Kelvin, pressure weakens. Gravity can begin to win, causing the cloud to contract. As it contracts, it heats up slightly, but if the heat can be radiated away, the contraction continues until stars form. The temperature of a nebula depends on several factors. External heating sources like nearby stars can warm a cloud through radiation. Inside the cloud, cosmic rays provide a steady heating source, colliding with atoms and molecules and depositing energy. Chemical reactions, particularly those occurring on dust-grained surfaces, can also release heat. Cooling comes primarily from radiation. When atoms or molecules collide, they can become excited, with their electrons jumping to higher energy levels. When these electrons fall back to lower levels, they emit photons, carrying away energy. Different elements and molecules have different emission lines, cooling the gas at different rates depending on its composition and temperature. Magnetic fields play a subtle but important role in nebula physics. The interstellar medium is threaded with weak magnetic fields, typically a few microgauss in strength, about 1,000,000 times weaker than Earth's magnetic field. But despite their weakness, these fields affect the behavior of ionized gas. Charged particles, ions, and electrons cannot move freely across magnetic field lines. They spiral around the field lines instead, constrained to follow them. This gives the magnetic field an effective rigidity, providing additional pressure support against gravitational collapse. In some models, magnetic fields may be just as important as thermal pressure in supporting molecular clouds against collapse. But magnetic fields can also aid collapse under certain conditions. If the cloud is massive enough, and if neutral atoms can slowly drift through the field while ions remain tied to it, the neutral gas can separate from the ionized component. This process, called ambipolar diffusion, allows the neutral gas to collapse, even when magnetic fields would otherwise prevent it. Turbulence also shapes nebulas. The interstellar medium is not calm and static. It's stirred by supernovas, stellar winds, spiral density waves, and other disturbances. This creates a complex, turbulent flow pattern with eddies and vortices at many different scales. Turbulence can provide additional pressure support, preventing collapse, or it can create compressions that trigger collapse, depending on the circumstances. The chemistry within nebulas is rich and complex. In the coldest regions, molecules freeze onto dust grains, forming icy mantles. These ices can undergo reactions driven by ultraviolet light or cosmic rays, creating more complex organic molecules. When a forming star heats the surrounding material, these ices evaporate, releasing complex molecules into the gas phase where they can be detected spectroscopically. Astronomers have identified over 200 different molecular species in the interstellar medium, ranging from simple diatomic molecules like carbon monoxide to complex organic compounds with dozens of atoms. Some of these molecules are directly relevant to life, including amino acids and sugars. The chemistry occurring in nebulas may be the same chemistry that seeded the early Earth with organic molecules, potentially contributing to the origin of life. The ionization state of a nebula depends on the intensity of ultraviolet radiation. In H2 regions and planetary nebulas, where hot stars provide intense UV light, the gas is highly ionized. Hydrogen loses its electron, becoming H+. Other elements are also ionized to varying degrees. This ionized gas, or plasma, behaves differently from neutral gas, responding to electric and magnetic fields. In dark nebulas and reflection nebulas where UV light is weak or absent, the gas remains mostly neutral. Molecules can survive and chemistry becomes more diverse. This neutral gas is transparent to magnetic fields, allowing the field to provide support through its interaction with the small fraction of ionized material. The density of nebulas varies enormously. In the diffuse interstellar medium, densities are about 1 atom per cubic centimeter. In typical molecular clouds, densities rise to hundreds or thousands of atoms per cubic centimeter. In the dense cores where stars form, densities can exceed 1 million atoms per cubic centimeter. Even so, this is still far less dense than any vacuum we can create in a laboratory on Earth. These densities affect everything from the cooling rate to the star formation efficiency. Denser regions cool more efficiently because atoms collide more often, allowing energy to be radiated away. But denser regions also have higher gravitational binding energy, so more energy must be removed to allow collapse. The interplay between density, temperature, gravity, and pressure creates a complex parameter space that determines when and where stars will form. Observations across the electromagnetic spectrum are crucial for understanding nebula physics. Visible light shows us the ionized gas and reflected starlight. Infrared reveals the warm dust and embedded protostars. Radio waves map out molecular distributions and magnetic fields. X-rays expose the hottest regions like supernova remnants and pulsar wind nebulas. Each wavelength provides a different piece of the puzzle. Nebulas are part of the great cosmic cycle of matter. They're where the universe recycles its contents, taking the ashes of dead stars and forging them into new stellar systems. This cycle has been operating since the first stars formed, billions of years ago, and it will continue as long as there's gas to fuel star formation. The process begins with stellar death. When stars exhaust their nuclear fuel, they return material to space either gently, through planetary nebulas and stellar winds, or violently, through supernova explosions. This material is enriched with heavy elements created through fusion or produced in the supernova explosion itself. Initially, the universe contained only hydrogen and helium, created in the Big Bang. The first generation of stars, called Population 3 stars, formed from this pristine material. They were massive, hot, and short-lived. When they died, they seeded the cosmos with the first heavy elements. Subsequent generations of stars formed from gas that was slightly enriched. Each stellar cycle added more heavy elements, gradually transforming the interstellar medium from pure primordial gas into a chemically complex mixture. This process, called galactic chemical evolution, is ongoing. The metallicity of the galaxy has been steadily increasing over its lifetime. Our Sun is a relatively metal-rich star, containing about 1.4% heavy elements by mass. This indicates it formed from gas that had already been processed through multiple stellar cycles. The heavy elements in the Sun and its planets are the products of countless previous stars, born, lived and died over billions of years before our solar system existed. The enrichment isn't uniform. Regions with more active star formation, particularly areas with many massive stars and frequent supernovas, become enriched faster. Massive stars evolve quickly and return material to space rapidly, so their neighborhoods become metal-rich sooner. Regions with primarily low-mass stars evolve more slowly, as these stars live for billions of years before dying and returning material. This differential enrichment creates a gradient in metallicity across the galaxy. The inner regions, where star formation has been most active, are more metal-rich. The outer regions, where fewer stars have formed, remain relatively metal-poor. And the halo of the galaxy, containing the oldest stars, is the most metal-poor of all, as these stars formed when the galaxy was young and few stellar cycles had occurred. The recycling efficiency isn't 100%. Some material is locked up in long-lived stars like red dwarfs, which will burn for trillions of years. Some material is locked up in white dwarfs, neutron stars and black holes, stellar remnants that never return their material to the interstellar medium. Over time, the galaxy's supply of available gas is slowly being depleted, as more and more of it is locked into stellar remnants. However, galaxies can also accrete new gas from the intergalactic medium, bringing in fresh material to replenish what's been consumed. The Milky Way, for instance, is thought to be slowly accreting gas from smaller satellite galaxies and from vast clouds in the surrounding intergalactic space. This infalling material is metal-poor, diluting the enriched gas already present, but also providing new raw material for future star formation. The dust in nebulas is also part of this cycle. Dust grains are created in the atmospheres of cool stars, particularly red giants and AGB stars. As these stars shed their outer layers, the gas cools and atoms condense into solid particles, forming dust. Supernovas also create dust, though the extreme conditions make it difficult for grains to survive. Once ejected into space, dust grains grow by accreting additional atoms and molecules from the gas. They serve as catalysts for chemical reactions, providing surfaces where atoms can meet and combine. They absorb ultraviolet light, shielding molecules from photodissociation, and they radiate in the infrared, cooling molecular clouds and enabling star formation. But dust is also destroyed. Supernova shock waves can shatter grains. Stellar radiation can evaporate them. Over time, dust grains are cycled through creation and destruction, just like the gas. The overall dust content of the galaxy represents a balance between production in stellar outflows and destruction through various mechanisms. The planets around stars, including Earth, are built from this recycled material. The iron in your blood was created in a supernova billions of years ago. The calcium in your bones, the oxygen you breathe, the carbon in your DNA, all were forged in stars and released through nebulas. We are, quite literally, made of stardust, recycled remnants of stellar processes that have been operating since the galaxy formed. This connection between stars, nebulas, and life is profound. Without the cycle of stellar birth and death, the universe would remain hydrogen and helium. There would be no carbon for organic molecules, no oxygen for water, no silicon for rocks, no iron for planetary cores. The existence of planets like Earth and the life upon them depends entirely on nebulas and the stellar cycles they enable. As you drift towards sleep, consider the nebulas we've explored tonight. Those vast clouds of gas and dust scattered through the galaxy like cosmic brushstrokes. Each one a stage in the endless cycle of matter and energy that shapes the universe. Birthplaces and graveyards, beginnings and endings, all woven together in the patient, ancient dance of stars. The Orion Nebula, glowing in the sword of the hunter, where thousands of new stars are being born right now, emerging from their dusty cocoons to light the cosmos. The Crab Nebula, expanding shell of a long dead star, its pulsar heart spinning 30 times each second. The Horsehead, silhouetted against glowing gas, slowly eroding under the patient work of starlight. The Helix, the eye in space, the gentle breath of a dying star expelled into the void. These are not just distant objects. They're connected to us through time and matter. The atoms in your body passed through nebulas once, perhaps multiple times, cycling through stars and back into space over billions of years. You are part of this cosmic story, built from stellar ashes, arranged by chance and chemistry into a form capable of contemplating its own origins. As the universe continues its slow evolution, as galaxies rotate and stars are born and die, the nebulas will remain. Not the same individual nebulas, those are temporary, fleeting on cosmic timescales. But the process continues, the cycle renews, and there will always be clouds in space, places where matter gathers and transforms and becomes something new. Rest easy knowing that you are part of something vast and ancient, connected to every star and nebula through the shared history written in atoms. The universe made you, quite literally, and someday when you return to dust, those atoms will continue their journey, perhaps finding their way into a new nebula, a new star, a new world. The cycle continues, endlessly, beautifully. Sleep well. And if these cosmic journeys help you rest, if they provide a peaceful way to end your day, please consider liking and subscribing. It helps others find their way here too, one quiet mind at a time. Until next time, may your dreams be filled with stars. Nebulas reveal themselves differently to different observers depending on the tools we use to study them. The human eye, looking up at the night sky, even from the darkest location on Earth, can perceive only a handful of nebulas. The Orion Nebula appears as a faint, fuzzy patch. The Lagoon Nebula might be visible as a misty smudge in Sagittarius. To Southern Hemisphere observers, the Eta Carinae Nebula glows softly in Carina. These are among the brightest nebulas in the sky, and even they appear as mere whispers of light, grey and indistinct, nothing like the colourful images captured by telescopes. This discrepancy exists because the human eye is remarkably insensitive to faint light, especially in colour. The rod cells in our retinas, which provide our night vision, are quite sensitive but see only in shades of grey. The cone cells, which detect colour, require much more light to function. When we look at a faint nebula through a telescope, we're typically seeing it with our rods, perceiving it as a pale grey cloud against the black of space. The vivid reds, blues and greens visible in photographs come only with long exposures that accumulate far more light than our eyes can gather in real time. Early astronomers working before the age of photography had to rely entirely on visual observations. They sketched what they saw through their telescopes, trying to capture the subtle shadings and structures of nebulas on paper. These drawings, while impressive given the limitations of their instruments, missed much of the detail that later became visible through photographic plates. Photography revolutionized nebula studies. By mounting photographic plates at the focus of telescopes and exposing them for hours, astronomers could accumulate light far beyond what the eye could perceive. Faint structures emerged, colors appeared, details invisible to direct observation revealed themselves. The first photographs of the Orion Nebula, taken in the late 19th century, showed structures and complexity that no visual observer had ever described. Modern digital cameras and CCD sensors have pushed this even further. These devices can detect individual photons with remarkable efficiency. They can record light across a wide range of wavelengths, from ultraviolet to infrared. Long exposures measured in hours reveal nebulas in exquisite detail, with colors representing actual physical properties of the gas and dust. But color images require some interpretation. Most astronomical cameras don't record color directly like your phone's camera does. Instead, they take separate images through different filters, each allowing only a narrow range of wavelengths to pass. An image might be taken through a red filter that passes hydrogen alpha emission, then through a blue-green filter that passes O3 emission, then through other filters for different wavelengths. These individual filtered images are then combined into a color picture. The hydrogen alpha might be mapped to red, the O3 to blue-green, and other emissions to various colors. This creates the stunning false color images you often see of nebulas, where different colors represent different elements or physical processes rather than the literal colors your eye would perceive. Some images use a technique called narrowband imaging, where extremely narrow filters isolate specific emission lines. The Hubble palette, a common technique, maps sulfur to red, hydrogen alpha to green, and O3 to blue. This creates images with colors quite different from reality, but that beautifully reveal the distribution of these elements. The famous Pillars of Creation image uses this technique, giving the pillars their distinctive golden brown color against a teal background. Infrared observations pierce through the dust that blocks visible light. Telescopes like the Spitzer Space Telescope and now the James Webb Space Telescope can see through the darkest nebulas, revealing the warm embedded protostars and the warm dust illuminated by nearby stars. In infrared images, what appears as an opaque dark cloud in visible light resolves into a complex landscape of glowing dust filaments, hot spots marking forming stars, and intricate structures shaped by stellar winds and radiation. X-ray telescopes reveal the hottest components of nebulas. Supernova remnants with their million-degree shock-heated gas shine brightly in X-rays. The Chandra X-ray Observatory has imaged many remnants, showing their shells, their pulsar wind nebulas, their jets and filaments in unprecedented detail. Young stellar clusters also emit X-rays as their strong magnetic fields and vigorous activity create hot plasma coronas around the young stars. Radio telescopes map the cold molecular gas in dark nebulas and molecular clouds. By tuning to the frequencies corresponding to specific molecular transitions, radio observations can measure temperatures, densities, velocities, and compositions throughout these clouds. They've revealed the detailed structure of stellar nurseries, showing where gas is collapsing, where protostars are forming, and how material is flowing through the cloud. Each wavelength provides unique information. Visible light shows ionized hydrogen and reflected starlight. Infrared reveals warm dust and embedded stars. Radio traces cold molecular gas. X-rays expose the hottest regions. By combining observations across the electromagnetic spectrum, astronomers build comprehensive models of nebulas, understanding their structure, their physics, their chemistry, and their evolution. The study of nebulas has also revealed their role in the larger structure of galaxies. Nebulas aren't randomly distributed. They're concentrated in spiral arms, those graceful curves that wind outward from galactic centers. This is because spiral arms are regions of compression, where gas clouds encounter density waves traveling through the galactic disk. As a cloud enters a spiral arm, it's compressed by the increased density. This compression can trigger collapse, initiating star formation. Massive stars form quickly and illuminate the cloud, creating emission nebulas that trace out the spiral arms in images of external galaxies. By the time these stars die, several million years later, they've moved out of the spiral arm due to the galaxy's differential rotation. This is why spiral arms appear rich in bright nebulas and young blue stars, while the regions between the arms contain older, redder stars. In irregular galaxies and starburst galaxies, nebulas appear in more chaotic patterns, reflecting the disturbed nature of these systems. Starburst galaxies, which are forming stars at prodigious rates often due to galactic collisions or mergers, are filled with giant emission nebulas, vast H2 regions containing thousands or even millions of young stars. The 30 Doradas Nebula in the Large Magellanic Cloud is an example of such a region, one of the largest and most active star-forming regions known. Studying nebulas in other galaxies provides context for the nebulas we see in the Milky Way. We can observe entire galaxies from outside, seeing the distribution of star-forming regions across the whole disk. We can compare nebulas in galaxies with different metallicities, different star formation rates, different morphologies. This comparative approach helps us understand the factors that control when and where nebulas form and how they evolve. Some galaxies show almost no nebulas or ongoing star formation. These are elliptical galaxies and lenticular galaxies, systems that have exhausted most of their available gas. Without fresh gas to fuel star formation, these galaxies grow old and red, their stellar populations aging without replacement. They serve as a reminder that star formation, and the nebulas that enable it, require a ready supply of gas. Once that gas is consumed or expelled, the stellar nurseries close, and the galaxy enters a passive phase. The Milky Way still has substantial gas reserves, enough to continue forming stars for billions of years into the future. But eventually, perhaps 10 or 20 billion years from now, much of that gas will be consumed. Star formation will slow and eventually cease. The nebulas we see today will have long since dispersed. The youngest stars alive then will be ancient red dwarfs, slowly cooling over trillions of years. The galaxy will grow dim and quiet, a museum of stellar remnants rather than a living star-forming system. But that endpoint is far in the future. For now, the Milky Way remains vibrant, with nebulas scattered throughout its spiral arms, birthing new stars that will shine for billions of years. And we, living in this active epoch of galactic history, are fortunate to witness this ongoing creation, to see the universe renewing itself through the patient work of nebulas and the stars they create. Our understanding of nebulas continues to evolve. Each new telescope, each new wavelength accessible to observation, reveals additional layers of complexity. The James Webb Space Telescope, launched in late 2021, is already returning unprecedented views of stellar nurseries, piercing through dust with its infrared vision to reveal forming stars and protoplanetary disks in exquisite detail. Future missions will continue this work, studying nebulas with ever greater sensitivity and resolution. Theoretical models have also advanced dramatically. Computer simulations can now model the collapse of molecular clouds, the formation of stars, the evolution of supernova remnants, all in 3 dimensions with sophisticated physics. These simulations help us understand processes that occur over timescales far too long to observe directly. They reveal how magnetic fields shape clouds, how turbulence affects star formation, how supernova feedback regulates the birth of new stellar generations. Nebulas also fascinate amateur astronomers and astrophotographers. With modern equipment, backyard observers can capture images of nebulas that rival professional photographs from decades past. Long exposure images, taken with modest telescopes and CCD cameras, reveal the Orion Nebula's delicate tendrils, the Veil Nebula's gossamer filaments, the Heart and Soul Nebulas in Cassiopeia. These amateur efforts contribute to our appreciation of nebulas, making their beauty accessible to anyone willing to point a telescope skyward and wait for photons to accumulate on a sensor. The names we give nebulas often reflect what we see in their shapes. The horsehead, the eagle, the butterfly, the cat's eye, the helix. These names make nebulas more relatable, turning abstract clouds of gas into recognizable forms. But they also remind us that we're viewing these objects from a specific vantage point. From another angle, the horsehead might not look like a horse at all. The shapes we see are projections, 2-dimensional shadows of 3-dimensional structures extending across parsecs of space. This is part of the charm of nebulas. They exist in the realm between the familiar and the alien. We can see shapes that remind us of earthly things, horses and eagles and eyes. Yet we know these are clouds of gas and dust floating in the void. Places where temperatures approach absolute zero and densities are lower than the best vacuum we can create. They're both comprehensible and incomprehensible, beautiful and strange, inviting us to imagine what it might be like to float among those glowing clouds, to witness star birth from within the nursery. Of course, actually visiting a nebula would be profoundly disappointing to the naked eye. Remember that these clouds are extraordinarily diffuse. Even in the densest cores, the material is spread so thin that it would seem like empty space to any visitor. You could fly through the Orion Nebula and barely notice you were in it. The glow we see in photographs requires accumulating light from vast volumes of space, something our eyes cannot do in real time. But perhaps that makes nebulas even more remarkable. These faint whispers of matter spread across light years somehow give rise to stars. These tenuous clouds, barely distinguishable from vacuum, are the wombs of creation. It speaks to the power of gravity, the patient accumulation of small effects over immense times and distances, the way the universe can take almost nothing and transform it into blazing suns. As we prepare to close this journey through nebulas, reflect on what these clouds represent. They're evidence of a universe in constant transformation, where nothing is permanent, where death gives rise to new life, where matter cycles endlessly between different forms. Stars don't last forever, neither do nebulas, but the cycle continues, and through that cycle the universe grows richer, more complex, more interesting. The first generation of stars formed from pure hydrogen and helium. They lived brief, violent lives and died, seeding space with the first heavy elements. The second generation formed from slightly enriched gas, and they too died, adding more elements to the mix, each cycle built on the previous one, gradually transforming the cosmos from its primordial simplicity into the chemically rich environment we inhabit today. Without this cycling, Without nebulas to gather material and birth new stars, the universe would be static and sterile. There would be no planets, no chemistry beyond simple hydrogen and helium compounds, no possibility of life. The existence of complexity, of richness, of life itself depends on the deaths of stars and the nebulas that recycle their remains. This is perhaps the most profound insight nebulas offer. Creation and destruction are not opposites but partners. Death is not an ending but a transformation. The atoms in your body have died many deaths, passed through many stars, been scattered by supernovas and planetary nebulas, drifted through space as cosmic dust, been gathered into new clouds and finally found their way into the molecular cloud that birthed the sun and earth. You are made of recycled stardust, and when you die, your atoms will continue their journey, perhaps someday becoming part of a new nebula, a new star, a new world. Rest in that knowledge. You are connected to the cosmos in the most literal way possible, built from its substance, shaped by its laws, part of its ongoing story. The nebulas we've explored tonight, distant and vast as they are part of your ancestry. You came from them ultimately, and to them you'll return in a sense when your atoms scatter once more into the universe. Sleep peacefully, knowing you're part of something vast and ancient and endlessly renewing. The universe made you to see itself, to wonder, to understand. And in that understanding, you complete a circle that began billions of years ago in clouds of gas and dust, in nebulas much like the ones we've visited tonight. May your dreams be filled with stars, with color, with the quiet beauty of cosmic clouds drifting through the dark. And may you rest easy, cradled by the same forces that shape nebulas and birth stars, the patient, ancient forces of gravity